All right, hello everyone. My name is Brian Mastenbrook. I'm CTO of Wearable Incorporated. We are a company out of Chicago that makes small portable wireless devices, and we use Racket in production. Now, what does it mean to use Racket in production, or anything in production? When people talk about using something in production, they usually mean it's deployed on a live server, or customers are actually using this right now. But when we talk about using something in production, we are actually using it to make something. So what is it that we're making here? We're making portable wireless flash drives. Now these things are very cool, but they're not the subject of the talk. They're basically little WebDAV-based network-attached storage devices that run in your pocket. They're useful for lots of things. You can connect to them from your smartphone, from your tablet. You can stream video from them. You can copy all the photos you took on your vacation to them to make a backup copy. You can put an SD card in one and get all the photos off your camera into your phone and then tweet them out to the internet, especially if you're taking lots of photos of your cats. Lots of great things. But these things don't run Racket. They have 128 kilobytes of RAM. Not a great environment for that. But we do use Racket to make these things. Now, how do you make consumer electronics? Well, you send a contract manufacturer a lot of parts. Tens and thousands and hundreds of thousands of little parts. A miracle occurs, and then profit. So, one thing you'll probably get from this talk today is that all startups use the underpants gnomes analogy. Because we're all in this phase, which is that crossing the chasm thing, trying to figure out what's between here and profit. Now, the contract manufacturer puts the pieces together, you tell them how to make it, and how to test it. And when we talk about testing, if what you're making is very simple, it's very simple to test. You plug it in, you flip the switch. If the red light comes on, it's good. If the red light doesn't come on, something's probably bad and you need to send it back and have somebody look at it. But when you're making something that does a lot of very disparate things, you have a lot of manual test steps. Now, what do we know about manual testing? Manual testing is hard, is error prone, is time consuming. You want to automate that when you can. So, automation in manufacturing, well, a lot of people at our company come from a company called Motorola. And at Motorola, we were indoctrinated into the fraternity of Sigma, 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 Sigma. Also known as Six Sigma for short. Now, Six Sigma's got a lot of acronyms and stuff going on there, but you don't really need to know all that. What you really need to know is that you design your products to reduce the complexity of manufacturing, you test everything you can before it leaves the factory, and that upfront investment in quality can save you money overall. And that's because when we talk about quality, there's very different things going on between software and hardware. In software, we talk about whether our test passed or not. But in hardware, we talk about defect rate. You are never going to get to completely perfect hardware because you're manufacturing lots of these, there's lots of variations. You'll get bad parts, you'll get parts that got put on wrong, you'll get parts that get knocked off when somebody's trying to put it into the enclosure. All sorts of things will happen. So there will be a defect rate. Now, when things go wrong in software, the user might get an error message. But when things go wrong with your hardware, you're going to have a product return, which ultimately costs you money. And when things go catastrophically wrong in software, you might get a seg fault. Nobody wants that. We try and avoid that. We call that property safety. But when things go catastrophically wrong in hardware, we call that a recall. And recall is a four-letter word. It's got more letters there, but ignore that. It's a four-letter word. Nobody wants to hear it. So you want to do everything you can to make sure that your product actually works. So, what do you need? You need something that can take these devices. Well, and first you have to actually tell them what to do. When they come off the manufacturing line, they're blank. They don't know what they are. They're a device sitting there saying, give me software. So you have to program them to do something. You also have to test them. And testing has lots of steps, as I showed in that slide. And you have to control the process as well. Because what we do is we license our technology to third parties, companies like SanDisk, for instance. And then we get paid on the basis of the units that they make. So we want to make sure that we're in control of the process, but we also want to be able to do things like ship new firmware on new devices, and we want to do that without having to send somebody to China back. So, when we test, we got a lot of things that we want to test. We want to test that the USB on these devices works. We want to test that the CPU works. We want to test that the SD card works. We want to test that Wi-Fi on them works, because these are wireless devices. And we want to test that the devices can run on battery power. So what did we do to solve this particular problem? Well, we built a test fixture, and we used Racket for that test fixture. So what we had to do was to define how we were testing these devices, and as we were doing that, we had to write little bits of firmware code that ran on the device that talked to something running on another device, the test fixture device, in order to validate that certain pieces of functionality were working. Because something on the test fixture can't go directly probe and say, test all the internal memory in the device and make sure it's good. It has to send a command that says, okay, go ahead, do this test now, and get back a status. So we needed to have two people working in parallel, building up a test system. And in order to do that, we needed a flexible, expressible language so that these two people working together could quickly and incrementally build up a very powerful system for running all these tests. It needed to be a safe system. It needed not to crash and go wrong in and of itself, because that will just cause bad units to get passed out the door. We really wanted it to have a built-in cross-platform GUI library. We've heard a little bit about that today. That's a really great thing that Racket has. We needed a database library. We needed low-level networking, UDP. And we needed something that we could quickly pick up and actually get the job done in. And Racket turned out to be a really great tool for that job. So we made a test fixture. And the first version of that test fixture is an embedded fanless computer. And this computer connected up to 5 devices under test. It put them in a little RF isolation box. So the operator put them in this box, closed the lid, and then once the lid on that box was closed, there was a little sensor attached to there that went in and actually fired an event back to the PC, which went back into our Racket program and said, okay, the lid's now closed. We're going to go ahead and test that the wireless works correctly. And we tested this in an isolation box because we were trying to test to see, did this device work with a very weak Wi-Fi signal? And if you do that outside an isolation box, then somebody's phone is going to disrupt the test when it tries to go scan for Wi-Fi networks or talk to a Bluetooth headset. And on this device, in order to test that the batteries on the device worked, since these devices were all plugged into USB power, we had to cut out the power. So we had a little set of devices that are called CRIOs from SparkFun connected there. They talk on a serial port, and we had our Racket program talking to these CRIO devices, controlling relays that would turn off the power to the device and make sure it could still talk wirelessly without power being applied to it, so the battery worked. And it worked pretty well. But we used a USB hub to connect all these things together, and USB hubs kind of suck. They will flake out after a while, they'll get confused. Linux will get confused as to what ports you're plugging into them after a while. Eventually devices will stop enumerating and everything grinds to a halt. But on the other hand, modules and contracts are really great. Before doing this, most of the people at our company used to work in a team at Motorola. And in that team at Motorola, we used Common Lisp for writing compilers. And one of the things we kept running into is that whenever anything went wrong, the end user got an error message that was nil is not of type real. And that was the only error message that they usually encountered, because usually they only saw errors when things went catastrophically wrong. And it was completely incomprehensible. So modules and contracts helped us to understand exactly where things went wrong. It was very good at catching mistakes up front that otherwise would have showed up rarely later on. But one computer controlling these devices, with or without a hub, wasn't going to scale. So maybe we need a distributed system. So we defined a new system. This is a test fixture 2.0, and it works pretty well. This is what's currently deployed right now, manufacturing those little SanDisk devices that you saw on that slide, and churning them out by the, well, I'm not going to say the number, but quite a lot. And this is a distributed system of BeagleBones. Each BeagleBone controls just one device, so no hubs, and a controller BeagleBone handles all the shared state, talks to the database, does all that wonderful stuff. And, yeah, question? A BeagleBone is a little ARM computer. It's from TI. It's kind of like a Raspberry Pi if you've ever seen one of those, but the hardware's a little bit different on it. And here's a picture of this setup. I'm not sure if you can see this very well, but over here we have a controller bone. And then there's these two little pairs, which is just how they're boxed in together, of BeagleBones. And each one has a display on it. And when new devices come off the line, they get plugged into one of these. And this device then goes and talks to the controller, sends a message over an SSL socket that says, hey, I need a serial number for this device. And the controller says, okay, I've allocated you this serial number. And it goes ahead and tells the device under test, okay, I'm testing you and your serial number is this. Well, it didn't go so well. We had some problems with that architecture. BeagleBones kind of suck. Turns out that the USB subsystem in the Linux kernel for that particular chip, that TI processor that's on there, is not terribly robust, and TI didn't really finish writing it and kind of punted it out to the community, and the community never finished it. Distributed systems, on the other hand, are great. They recover automatically when things crash. And it turns out every once in a while our controller does crash because something, we haven't found it yet, is leaking memory very slowly, and eventually we hit the Racket memory limit, which is on there for a very good reason, but we do hit that limit. The controller crashes, and then, well, all the programmers sit and wait, and they recover just fine when things crash, but it doesn't tend to inspire confidence in the system when you're sitting there waiting for a controller that's crashed to come back up. So, test Fixture 3.0, which we're designing right now, back to the PC, server class hardware, hopefully we'll get this right this time, 16 independent USB controllers, no hubs, Wi-Fi and Bluetooth for testing all sorts of new Internet of Things devices that are coming up here. Great stuff. What are the invariants of the versions of these things? Well, we got a lot of events and stuff going on asynchronously. When the operator is plugging devices in, that device shows up and gets enumerated by Linux, and we get an event that says, hey, this device just appeared on the USB bus. Well, that comes in, and we've got to go and correlate that to the USB, basically where it is on the USB bus to say it was plugged into this slot over here. We got to go tell it to program. At some point later, that programming process is going to be done. It's going to connect to a Wi-Fi network. We're going to get a message from it. All sorts of stuff going on asynchronously. We need to be robust to unexpected conditions because we're testing hardware that might not be good. So things may hang on the USB bus for seconds at a time if something is wrong. Crystal on the device is knocked out, something like that. Things may go wrong in all sorts of bizarre ways, and you need a system that's going to be tolerant to all sorts of unexpected inputs. And it needs to always work, because in the end, if this thing doesn't work, then you can't actually manufacture a product, and then nobody gets paid. So in a sense, this is the most business critical thing we do, because this is the thing that actually keeps product getting churned out and keeps the lights on. So, how do we handle all of that asynchronous stuff going on and make sure we can keep track of what's going on when? Well, our process of programming and testing is a process that goes through a number of states. And each one of these programming processes that's going on is completely independent of the others, but they're all communicating with several shared things asynchronously. So there's a UDP socket listener on the outside that's waiting for UDP messages, and when it gets UDP messages, it finds the right programming process associated to it by its serial number and says, hey, I got a message from you that came in from this device because we're testing the Wi-Fi, and the way we're doing that is we're bouncing some UDP messages back and forth with each other. So actors help us keep track and coordinate all that stuff. And in our model, actors are Racket threads, and Racket threads are great. They're green threads, they're not native hardware threads, but because Racket takes care of all the details for us, we don't really worry about scaling this. We don't really have performance problems with this. They exchange messages with each other, they encapsulate state, and we've got some different types of actors that we use. We have a controller actor that is responsible for things like assigning serial numbers to devices under test and tracking which ones have actually been manufactured correctly, which are good. We have programmer actors, which are responsible for programming and testing a single unit. We have GUI actors, which are responsible for updating the display of state to the operator of the test fixture. And we have some that are responsible for proxying external interaction, like that UDP actor I was just talking about. Now, when we started working on this, typed scheme, as it was called then, was not really in a state where we could use it. But that's fine. We used modules and contracts were great. When it came time to do version 2, I told David, who was the employee of ours who was doing most of this writing, you should really look at Typed Racket. It's really, really great. And so we started using it. We started typing some of our modules, and along the way, we ran into some issues when we actually tried to create deployable executables with those, and we were running into a crunch on actually getting the project done. So in the end, we pretty much just macroed out all the types, left them in the code, and deployed as untyped. Type 3, version 3 here, we have moved most all of the code to Typed Racket, but we're not entirely using types to describe everything we're doing. Yes?
You mentioned that you have GUIs in your world.
Yes.
And the GUIs are presumably within the GUI framework or the GUI classes.
Yes.
How did you cope with those in the type version?
We've got a zillion types that we've done, not completely for the GUI framework.
So that is leftover untyped stuff.
Well, there's some leftover untyped stuff, but we actually do have types for a number of the GUI calls. Yes, but I hear there's a more principled approach going on right now, so I'd be very happy to delete that file when we're all done. So what we have now is that our modules are typed. The messages that actors exchange with each other are also typed, but there's still some dynamism in the system that could be replaced with types with regard to the actual states that these things pass through. Because we're basically modeling these things as state machines, the states currently are being looked up dynamically, which is how we started here and how we're continuing to do it. So typed messages, what do they look like? Well, they're very simple. Here's a ping and a pong. When you send a ping, we put an X in there as a number that just says, okay, here's my current sequence count. You get a pong back. I didn't put the X in there, it's just a pong. Here's another message example, a set target that says, here's who you're going to be talking to, and it takes a thread. State machine then basically has a couple of state variables that are private to it that can be set at initialization or later on. It has an initial state, and it has a state that you go into when there's a problem, when something goes wrong. And that's your chance to recover and try and do whatever it is you need to do in order to actually make it work again. Because as I said, the system needs to always work. So, now that we have a state machine, how do we get between states here? Well, here's a state. There's no timeout on this state. When we enter the state, we don't have really anything interesting to do when we get into the state here, but we have a transition. When we get that message that says set target, I left a printf in there, but you set the target, which is associated with your context, that's your state machine, to the T out of the message you got in, and then you go to a new state. And in that state, you can do all sorts of wonderful things and transition between multiple different states. So how does this actually work? Well, let's do a demo here. And I appear to be in a situation where I don't have display mirroring. Oop. So here we are. We have our messages. We have our types on here. We have our state machine. We have our start message. And then we have a send ping state. And the send ping state is very simple. When you get into it, you increment that value that you're keeping around that's just kind of being sent in the message, because why don't we put an int in there? And we send it out to our target, and then we go to a state where we're waiting for a pong. And when we get the pong, we get a ping, we reply to it with a pong. That's so that we can have two of these talking to each other. When we get a pong, we go back to the send ping state. So when we run this, we can go ahead and make two of these things. We can then tell them, okay, your target is the other one, vice versa. And when we run these, it doesn't run the way I was expecting. Well, what's a demo without it working? Okay, that's fine. I have a more complicated demo. That one I know works. So this one, our ping ponger is still pretty close to the way it was here. But we have another state machine called the ping responder. And all it does is just respond to pings. So it's sitting there, it's waiting for pings. And when it gets a ping, well, actually there's a callback on this thing. And it calls the callback to say, okay, I got a ping. You can do whatever it is you want with that information. And put a new line in so this is a little easier to read. Re-indent or something. And you call your callback with the number that you received and a thunk that will go ahead and actually send the reply to that message. Now, we can, run the demo and it'll do what it does. But we can also then say, oh, well, here's an untyped module. And this untyped module is a GUI thing. So here we have a frame and a message and all this wonderful stuff. And what we're going to do, we'll go ahead and run this. Well, we got a ping with 1 in it. And our button lets us send a pong. We send the pong back, we get another ping with a 2 in it. Keep doing this. Well, we've built a counter. Well, let's show how this is really asynchronous here. Let's go ahead and take this state machine. And what we're going to do is when we're in the await pong state, or rather when we're in the send ping state, we're not going to send the ping immediately. Right now what this is doing is a send ping state basically sends a ping and then organically transitions to a new state, which is await pong. But what we're going to do instead is we're going to make this happen after a timeout. So now what we're going to see is that whenever it goes into the send ping state, I'll make this 2 seconds. Oop. That was just the state machines. Right, now we're awaiting our first ping and we got a ping. We send a pong, we can't send another pong yet until we get a ping back in, but after 2 seconds we get another ping. Wait, now another ping comes back in. So this shows how the asynchronous events are working with each other, and on the other hand, we've got this GUI code on the outside. It doesn't really see the state machines, but we're able to keep the GUI up to date, and we're able to do so by firing off messages at some other state machine that is basically proxying the GUI for us, so that our programmer classes don't really understand anything about the GUI. They're just saying, okay, I have successfully programmed another part of the device, update the status. Yes?
Did you say channels or channels?
No, we're not doing anything that crazy. I'd have to think about it. It's slightly possible, but I'm not sure. So, is it time?
You can wrap up, yeah.
Okay, well that was pretty much the end. So lessons learned, modules and contracts are great. Types are even better. Let's see if I can. Yes, macros are. My presentation's coming. There we go. Macros are absolutely awesome, and work very hard to find the right encoding for your problem domain and work at the highest level you can, because that's the only way you're going to be able to get complicated stuff done in short order with a small team. All right.
So you have time for maybe one question while Tony plugs his laptop in.
Somebody other than that. Yeah.
Did you consider using other paradigms than actors?
We actually have a lot of experience with actor models, so not terribly much.
We have a type language for exchanging messages with a language almost identical to yours, with just slightly about it. That's all.
Okay.